Bueno, es un gusto presentarles hoy para el coloquio al ingeniero Luca Cabral, que está realizando la tesis doctoral en ingeniería entre el IAR y la Facultad de Ingeniería, el Instituto de Investigaciones en Electrónica, Control y Procesamiento de Señales, del grupo de Carlos Muravchik, siempre me confundo. Luca se recibió de ingeniero con un proyecto del doctor Federico Guerrero en la Facultad de Ingeniería y ahora ya hace 2 años prácticamente que está realizando la tesis doctoral para ser aplicada en el proyecto insignia del IAR, que es el instrumento Multipurpose Interferometer Array, o como nosotros lo conocemos, MIA. Luca va a hablar un poco de los trabajos que está haciendo, pero al principio va a contar un poco la primera parte de su trabajo de tesis y luego se va a dedicar a la parte del diseño de correladores de este MIA. Así que bueno, su tesis doctoral está siendo dirigido por quien les habla y por Mariano Fernández Corazza del LACY y también por Guillermo Gancio, con el cual trabajo intensamente. Gracias.
Bien, un primer comentario que es que como hay gente que también está de lejos mirando, como para que puedan entender todos, voy a dar la presentación en inglés. Okay. So, first I will introduce the project where I am working, which is a Multipurpose Interferometer Array, MIA, which is an interferometer to be built in 3 phases, where in the last phase we consist of 64 antennas. It will be placed at a geographical latitude of minus 35.5 degrees. In its last phase, we want to achieve a 1 arc-second resolution at a center wavelength of 21 centimeters. And now there is under construction a pathfinder which consists of 3 antennas. So, what is an interferometer is the first question. So, principally we have 2 antennas which make a baseline, and both antennas point to a desired astronomical source. So, we make our signal taking both outputs of the antennas and then doing a correlation. So, if we think in a monochromatic signal, which is the incoming signal to our antennas, and then we do this correlation, we notice that the output is proportional to the power of the incoming signal, and also it's a function of the baseline made by the 2 antennas, and also the direction of the source. Well, moving to a more realistic case, we usually don't have a point source. We have an extended source with some random shape, like in this example. And also, we don't have a simple correlator that the previous slide. We have a complex correlator. So the output changed a bit to this expression. We call the output the visibility function, which is an integration because we don't receive only the information of a point on the sky, we receive the information about all the sky. And then this function here is a function, like in the previous slide, of the baseline and the place where we are pointing. Moving with some new parameters, we have that we can change this baseline, this product, for the components of the spatial frequency, which characterize the intensity of the sky, in this case is the spatial frequencies, which are denoted by U and B. And also we have the parameters here, which are L and M, who describes the source in the sky in a cosine angles. So this is why actually in this previous slide I lied a bit, because we don't actually measure the visibility of the sky source of the source in the sky. We measure only a few components. Why? Because as we can see with the letter in red of the baseline, the baseline is fixed. We don't, in principle, moving the antennas. So this that product is a fixed value. Because the baseline is a fixed value, also the U and V components on the Fourier plane are fixed. So we don't measure all the visibilities, only a few components. We only get a few information about our source. Because of that, we can do this schematic where we want to observe some astronomical source in the sky, and the interferometer makes a function, works as a spatial filter, only return some components after this correlation, we have at the output our measured visibilities. So my work in my PhD career is first the optimization, the design of this spatial filter, and also the design after this of the full correlator. Okay, so okay. Talking about this spatial filter, now I will define how it looks. So remember this, the measure visibility. We can rewrite this expression as a product of the real visibility of the source and this spatial filter. And now I will give an example of how it works. We have in the first column our model image, which can be a source, and its Fourier transform. And then we have the UV coverage. That UV coverage is our spatial filter in this case. And the measured visibility is a product, as we can see in this example. And then we have the measured visibility, in this case, the observed FFT, which can be seen how different it is with the model FFT. So when we perform the inverse Fourier transform, we can see that the observed image is quite similar to the real image, but it has a few components which differs because of this spatial filtering. Okay, another characteristic about this spatial filter is its inverse transform, which is the point spread function, or sin times beam. And we have another examples about that. So if we have some spatial filter, we can know or estimate how it looks, the beam. In this case, the first example is this uniform function, uniform and constant about a diameter. In this case, diameter of 2a. The beam has this square sinc function line. In reality, it's a Bessel function who has these characteristic sidelobes. Another common example is a Gaussian spatial filter, which transform. It's also a Gaussian beam in this case. Well, previously I described the filter and the spatial filter and its transform, but we have also need to define how I make that filter. So to know that, we know which are the baseline because we put the antennas, we place the antennas, so we can calculate which are the baselines. And as we see in the definition of the visibilities, we know that it is a function of the baseline and also the direction where the source is located. So we use the equatorial system, which is defined with the hour angle and the declination. So knowing the location of the source in the sky and the baselines, we can calculate the UV points that are we sampling. Okay, so we define the spatial filter. Now we have to make a problem to solve. We can solve the problem in mainly two ways. Maybe we want some beam shape, which is the second path, or we may define some UV coverage that we want. We choose the UV coverage because in the case of the beam shape, it's like a direct problem where we move the antennas until reaching this beam shape, but there is information in this way which we don't know. We know only after solving the problem, like how spatial frequencies we are sampling. In the case of the first part, we can know these parameters. So I justify why don't go for that way. Now I will justify why the UV coverage path. Here is another example of UV coverage. And in this example, we can define with a model, for example, which signal to noise ratio we want. In this example, we have these more red zones. These more red zones denotes a more sample region than this, for example, in the other ratio, which is lower red than the first one. In this case, because we sample more the region, we can estimate better, and we have a better signal to noise ratio. Another important parameter is the resolution. So the resolution of the beam, in this case, it can be seen with this, with the longest perimeter. The longest perimeter diameter is related to the resolution, and also is related with the longest baseline, talking in the ground plane where the antennas are located. And then another important parameter is the sensitivity of transmission. How big sources in angular size we can detect with our interferometer. That parameters are, we can estimate that sensitivity with this shortest perimeter circumference. And also, we can also define the beam shape that we want with the UV coverage. For example, if we propose some Gaussian UV coverage, like in the previous slide, we can also know that the beam that we will have is also a Gaussian beam shape. And then the shape of the UV coverage will change with our objectives. Both the position of the source in the sky and also the duration of our observation. And a longer observation will give us more points, so it's another UV coverage. Okay. So we define the spatial filter, we make a problem about that, now we have to solve it. And this is a gradient-based optimization, is the way we choose to solve this problem. And how is it? First, we have a vector of n components, which each component is one antenna. We have a function who takes this vector and gives us a real value. And only with that, we can say that with the gradient, we can know which is the minimum direction. So with this, we can say, okay, so if I displace all the antennas in that direction, I will reach the minimum, which is my optimal antenna distribution. So we made this optimization algorithm. So now we have to define which is that function. And here it is. This is the G function, which is the reference between a model, which is our objective, the model sample density, and the array density, which is denoted by the D. And rewriting the algorithm, we have this algorithm for snapshots. First, we have to add this M, which is the matrix transformation. This is an inverse problem because we define a problem in the Fourier plane, and then we have to go back. So we need this matrix transformation who goes from the U plane and goes to the ground plane. And then we have now this sum, which is because for each antenna we don't have only one sample. Each antenna has n-1 samples. So if in order to reach the model, which is our objective, we have to move all these samples for each antenna in order to reach the model. So for do that, we average over all the samples for each antenna, and then after that we displace the antenna in the minimum direction, in this average minimum direction. And this algorithm only works for a snapshot because this matrix transformation is dependent of our angle. So if we only observe for a couple of minutes, this matrix doesn't change. But if we perform longer observation, this matrix will change with time. Another parameter is this the convergence. We have to define a grid because this is a numerical method. So we start with a continuous problem, and if we don't do a well reading, we have the problem that the numerical derivatives will be null, which doesn't correspond with the problem, and also if we don't grid, we doesn't optimize anything. So because of that, we have to define a correct grid in order to do optimization. Okay, so we define a spatial filter, we make a problem, we propose a solution to the problem, and now the simulations. Remembering a bit, we have 64 antennas, and we want to achieve a 1 arc-second resolution beam. And in this first case, we are doing a snapshot, in this case, to the zenith. We use two models, which are the uniform distribution, the erosion distribution, and also a uniform distribution with terrain constraints. This terrain constraints it's an extra feature because maybe in the place where we are placing the antennas, we have forbidden zone regions where we can place. And the characteristic of the optimizer are rectangular grids of 10 lambda by 10 lambda, a constant gain of 0.1, and for all the cases we perform 500 iterations, which took an average time of 1 minute and 30 seconds. Okay, the first model was the uniform distribution, which can be defined only with the resolution that we want. So with that, we can define the model, and then after the optimization, we reach the solution. On blue, we can see the initial distribution, in red the final, and we had a circumference with a diameter which corresponds to the longest baseline of the optimized distribution, which in this case is 55 kilometers. With this first optimization, for a uniform coverage, we expect for previous result to reach a solution which is like this. We have this circumference, and all the antennas of the final distribution lays on this circumference. And we have also an inner core which makes the medium baselines of the UV coverage.
Sorry, what is the resolution that you?
This is 1 arc second.
One arc second.
Yeah.
Okay.
In the case of the Gaussian distribution, we have the model, which is, has a uniform Gaussian distribution, where the sigma parameter is defined by the full width at half maximum. In this case, we also expect a Gaussian distribution on the ground plane. We can see that we have an inner core with a lot of antennas, and then if we move out of this inner core, we see less and less antennas. In this case, to achieve this 1 arc second resolution, we need a baseline of 72 kilometers. And then we have the terrain constraint. We can see that also the final distribution of the antenna lays on this circumference, and in the case of the optimizer tries to put an antenna on a forbidden region, another function pulls out these antennas to the nearest boundary.
So another question.
Yep.
What is a forbidden region exactly in topography?
Topographically, for example, can be a hole, a veiling, for example, restricts forbidden region who belongs to a people, different people.
So how flat should be this region?
How flat?
Yeah.
Can be related to the shape of the zone, or for example, with the SHIM-RT, which has roots near, you can place there an antenna because there is a root and some other problems. So it can be different things. Okay, here we have the density, the coverage. In the first column we have the model densities, which are our models, and in the second we have the optimized density. The important here is that the second column has to be similar or equal to the first column. In the case of the uniform density, it needs to have the same color over all the diameter. In the third column, we can see the beam shape that in the first case, we can see that have the sidelobes, which are characteristic for this UV coverage. And in the case of the Gaussian beam shape, we don't have that sidelobes. And in both cases, it reached the 1 arc second resolution. So we can see that for the snapshot cases, the optimizer works. Now we move to the second optimization, optimizing 2, which is related for longer observation, because we don't only want to make a snapshot. We may want to do longer observation. So we have to do some redefinitions. One of them is the density, the array sample density. So this new density can be think as we do an observation, do these capital R observations. So we can define a lot of snapshots, and each one corresponds to a different hour angle. And this our new function to optimize is this GR, which are now not only one function to optimize, we have R functions to optimize. And then we have to change the algorithm, so it looks like this. Now we have two sums. The first is related to the matrix transformation, because we have more hour angles, so the matrix change with time. And because we have R samples, we have to sum about these R snapshots. So this can be seen that like now we are not only averaging on time, we also are averaging about space, because as the apparent position of the source in the sky change, the UV samples that are we measuring, sampling, change also in the UV plane. So we have to do this double averaging. Now that we rewrite this description, now we have to do new simulations. In this case, we change this snapshot observation for a 3-hour-long observation, taking 1 sample per hour. The models are the same, a uniform and a Gaussian distribution, and in the optimizer characteristics now change the amount of iteration for 200, and the average time for this case was of 44 seconds. Here, with the optimized distribution, we don't expect anything. That was the case of the snapshot observations. But here we can see that for the uniform distribution, the final distribution also lies on this circle. And now the longest baseline changed by 2 kilometers, longer than the previous case. And in the Gaussian distribution also fits with a Gaussian distribution of antennas in the ground plane. And in this case, for achieving this 1 arc-second resolution, we need a longest baseline of 67 kilometers. So in the coverage, we also fits the model. We have our uniform distribution and Gaussian distribution in the optimized density, and we still seeing this characteristic side lobe in the case of the uniform coverage. Both beams have the 1 arc-second resolution. So, conclusion, we implement this optimizer for a snapshot and longer observation, applying the 2 models, which are the uniform and the Gaussian coverage, considering this terrain constraint, and apply it to the case of MIA. For future work, first changing this rectangular grid for a polar grid, because for describing this problem, all the models has a radial symmetry, so a rectangular grid isn't appropriate for the problem. Adding some features like shadowing, which is a case when, for given declinations or hour angles, one antenna may obscure another one, so it's a problem to take account in this problem. And then we may do optimizations for a lot of hour angle duration observations and for a range of declination. So we have to compare all that optimization and take a decision about which is the more appropriate for MIA. So it's another problem to take account. So thank you.
As you know, MIA is a modular instrument. So the first step will consist of 16 antennas. So then you should implement an optimization for these 16. Then you will have this fixed array, and then you will add the remaining stations. So you will need to improve to a bigger array with a constraint of the former array. So how are you going to deal with this?
Thank you for that. I forget about the subarray optimization. This idea of the subarray optimization is also to take account this step. First, we'll have 16, then 32, and last 64. So in all the steps, the array may work with our expectation, following some model of density. So it's another thing to take account. That was the question.
So each sub-array will be a constraint for the next one. Let's say in the optimization.
We can define the final model as another sum of different model, each related for each step of MIA.
Okay, I understand. And another question, as you know, perhaps we can get some extra antennas for the Pathfinder here, 5, let's say, donations from Telecom. So what would be the optimal array for a configuration here of 8 antennas, and what is the resolution we can get with 8 antennas? Perhaps we should
Okay, with 3 antennas, we can make a distance of there is defined, I think, a distance which is the necessary to do the calibrations of the Pathfinder. Now, with 5 antennas, we can.
It depends also the distance between the most distant ones. That would be 100 meters, perhaps.
Yeah,
we can go in that direction.
Just 100 meters.
Wow, I guess.
But it is north-south. It is north-south. We need east-west.
Eh?
It is north-south. We need east-west.
It's better in the east-west case, so we can sample more components of the UV plane, so it's a better case. And the resolution will be defined with how far we can pull that antennas. So if Algo has a problem,
I was in that direction.
Okay.
You will have a better UV coverage with 8 antennas. But not so.
in that sense, more is better always.
Yes.
Okay. More questions?
Well, have you thought of, I guess not, but of having moving antennas, or they are going to be fixed?
They are going to be fixed. That is defined. Because of that, I didn't add to this case.
And what if you start adding moving antennas? I guess that the problem will be more complex, and why are you not simply because of money? Just because of that. But
Not only money, the whole system should be autonomous. So each antenna should have their own power station, probably solar power station. So you need to fix that. And the potential locations, probably the best one is in Malaga, Mendoza. So this is a private property. There is an agreement with the owners for the tanks of Auger. So the idea is to put the antennas very close to one Auger tank using the already existing agreement. But if you try to move the antennas, then you will pass from the land of one owner to the land of the other owner, and then that is a little problem. And it's, of course, much more expensive.
More questions?
But you can make interferometry with, for instance, the main array and these antennas here, but we are very far away.
Yes.
From probably other antennas, I don't know, probably in Argentina.
Yes. Maybe here maybe you have to ask some astronomers. But with that, first with one antenna, we can make, for example, an autocorrelation of the antenna and extend our sensitivity to our sensitivity to extended emission, because with only the full array we have the boundary of the shortest baseline, but using only one antenna with a longer diameter, which is the case of our antennas, we can we can use it in that way. And also,
And just putting a few, let's say 3, 4 extra antennas very, very far away, that is positive in some sense, or not?
Yes, always is positive because we have more samples, so and maybe we can characterize some lower angular size structures.
Mhm.
So maybe we may do some exhaustive study of the source, but we can do some differentiations on the difference of the structure of the sources.
It will also be tempting for global BLBI.
Okay, more questions? Well, if not, let's thank Luca again.